Okay, is that on? Yeah, sounds on. Okay, great. Well, thank you very much for the invitation to this exciting conference. I wanted to tell you about some math theorem that's joint work with Sam Gunningham, and I'm going to take the somewhat possibly misguided approach of trying to explain it as a physics result. So we'll see how that goes. So I'd like to give a kind of a setting, and the setting is going to be kind of a rough caricature of the idea of defects and moduli space of vacua in supersymmetric field theories, but seen from the point of view of someone doing topological field theory in the spirit of Ulrike Tillman's talk or John Francis's talk. So let me kind of give you a little bit of the setting of how I think about topological field theory. So there's some adjectives that go with a topological field theory. These are going to be extended field theories, and maybe these kind of infinity field theories appeared in Tillman's work. So I would like to approach the idea of, so in particular, an n-dimensional topological field theory has a bunch of data. It has a bunch of assignments that it attaches vector spaces, maybe differential graded vector spaces, to n-1 manifolds, attaches categories to n-2 manifolds, and a bunch of higher stuff we were going to ignore. But the way I'd like to understand a topological field theory is by studying its defects. So the first kind of defect we have is the idea of a local operator. We're studying, here's my n-dimensional space-time. I'm going to study local operators. These are things I can insert at points. And the way I'm going to encode these in the language of topological field theory is by taking the link of the point. I'm going to cut out a little ball, which is an n-1, boundary is an n-1 sphere. And so the space of states on the n-1 sphere in this topological field theory, that'll be the space of local operators. And the operator product expansion of local operators comes from taking 2 points and colliding them. So that gives you an operation which is, in dimensions 2 and more, is a commutative multiplication. You can take the 2 points and collide them this way, or you can move them around each other. And the higher the dimensions, the more directions you have to move. So you have kind of several different directions in which you can collide, but we're doing topology. Those are all the same, but they account for more commutativity. So technically, this is covered in the notion of an EN algebra, and kind of the physical manifestations of that we're working out physically with Chris Beam, Matt Bullimore, Tudor Dimofte, and Andy Knightsky. In particular, one of the phenomena that you get is that besides the commutative OPE, there's kind of a secondary operation where I can take this operator and kind of integrate it around kind of a residue operation. I can take one operator and move it in a little sphere around another operator. And that gives a Poisson bracket. So these algebras of local operators are always, in dimensions 2 and above, they're always Poisson algebras. Or more precisely, they're going to be in odd dimensions. They're going to be even Poisson algebras, usual Poisson algebras. In dimensions 2 and 4, they'll give you odd Poisson brackets. So I'm going to consistently ignore Z gradings. So I'm just going to try to keep track of even and odd. Okay? So that's the kind of structure one sees on local operators. If you go further down, there's a lot more structure, like John Francis was indicating, a lot more structure in a field theory that you can try to animate. So in particular, you can try to look at line defects, something you can have along a line in space-time, some kind of singularity. And again, we're going to encode that by looking at the link of this line, which is now an n-2 sphere. So in topological field theory, we attach a category to an n-2 sphere. And again, this category has a kind of a commutative multiplication corresponding to operator product expansion of line operators, collisions of lines, which again has some kind of modified commutativity, which is captured in this notion of En or En-1 categories. So that captures how commutative, how much room you have to move lines around each other. But to first order, it's just a commutative multiplication of this category. Okay, so that's kind of the kind of things we're going to be studying. What are we going to do with them? We're going to try to look at these algebras of operators, local operators and line operators. We're going to put them in an omega background. So my kind of TFT understanding of what an omega background is, I'm going to take a circle rotating space-time. So I'm only going to do kind of epsilon 1. I'm going to have only a single rotation like appeared in Lotte Holland's talk this morning. I'm going to have a circle that's acting on space-time x, and from the axioms of a topological field theory, you get that everything you measure in this field theory carries an action of this circle of rotation, and so you can take invariance, which means in the level of vector spaces means pass to equivariant cohomology. So we're going to study all of these operations of the field theory U1 equivariantly, where the U1 is acting on space-time. So what is the kind of operational meaning of that is that instead of having a single field theory, we have a bunch of, so instead of having a single vector space z of x, we have a family, this equivariant cohomology, a family parameterized by a parameter epsilon, which come from the equivariant cohomology of a point, or cohomology, if you like, of BU1, of CP infinity. So we're going to consider deformations of the algebras of operators coming from thinking about them S1 equivariantly. And one of the wonderful things about the omega background is that it destroys commutativity. Your algebras of local operators were commutative because you had a lot of room to collide. The more dimensions you had, the more room you have to collide. If I rotate around an axis, I kind of lose two directions to collide in. And so I lose, I'm going to go from some kind of Poisson algebra to some kind of less commutative algebra. And in the examples of three-dimensional field theory, this exactly corresponds to deformation quantization. I'm going to take an ordinary Poisson algebra. We'll have a deformation depending on a parameter epsilon. And this is going to be exactly deformation quantization of this Poisson algebra. So we're going to think of this extended field theory, operators in it, and putting them in the omega background as a way of encoding commutative Poisson algebras and its quantization. So I want to think of this as kind of a template to do the kind of things one usually does in representation theory, but it kind of embed them into this structure. So far, so good? Okay. I'm going to be pretending that, right, I mean, so I'm going to elide the difference between En and Pn, if you'd like. So I'd rather work on the chain level and say En, but I'm going to say the words Pn instead. So I don't think you should, I think it's better not, I prefer personally not to do that. So you can either take, on the level of cohomology, you get actually shifted Poisson brackets. On the level of chains, you get En structures. But for the purpose of this talk, I'm going to ignore the difference. Okay, so now I'd like to make some kind of caricature of moduli spaces of vacua as understood from the point of view of topological field theory. So again, I'm not going to have any access to a supersymmetric quantum field theory. I'm only going to understand a topological field theory that it comes from twisting it. And so I want to understand what kind of geometry can you extract, some kind of moduli space, out of this field theory, which I want to call the moduli stack of vacua. Maybe just put the word in stack, so my collaborator, Andy Netsky, gets very uneasy whenever I call this moduli of vacua. So this is just to put some unfamiliar, less familiar term to distance from it. So the way I want to think of this, this is a picture that we're developing with Andy Netsky. The way I want to think about the moduli of vacua is kind of like in this kind of Uneda way. It's a representing object. It's the thing of which your theory is thought of as maps into it. In some sense, I want to try to model my theory as sigma model into maps into some mythical space. That mythical space I'm going to call M sub z. So I'm not really going to try to define directly M sub z in a non-tautological way. I'm going to try to understand how do you measure this space? How do you see something physically about this space? And the way I want to understand the space is using defects. So the first thing I want to observe is I have a commutative ring, or maybe Poisson algebra, which is local operators. Now in algebraic geometry, you learn once someone gives you a commutative ring, you can build a space out of it, that's spectrum. So if someone gives you this commutative ring of local operators, I'll build a space, which I'm going to call M sub loc. It's the kind of the local operators shadow of the moduli space. Okay? So you can build a variety, M sub loc, just by declaring that functions on it are local operators. So the idea is that whatever the full moduli of vacua of the theory is, holomorphic functions on the moduli space of vacua should be given by local operators. This is an assignment of Vevs to local operators. So a local operator is going to give a holomorphic function on the moduli space. I'm just going to declare this to be my first approximation of the moduli space is the space that has these guys as functions. So whatever the moduli space actually is, the moduli space might not be an affine variety. So I might not actually capture this full moduli space, but I'll capture some shadow of it, as much of it is seen by functions. So this is called affinization. Take any complex manifold, you can look at holomorphic functions on it. You can make an affine variety out of that. And there's always a map. That might forget a lot of stuff. Okay? Does that definition make sense? Yeah. So that's a first space I can attach, concrete space I can attach to a topological field theory. again, maybe as a side comment, the real context in which these spaces live is in some mildly non-commutative form of derived algebraic geometry, which is this kind of EN algebraic geometry, which is developed in John Francis's thesis. So that's a place where these guys naturally live. But I'm going to just think of them as varieties. Okay, so that's what you can get out of local operators. The next thing you can do is, in a topological field theory, you have line operators. You have a category of line operators. It's a category with a tensor product. And the idea is that whenever I give you a line operator, it should give me a holomorphic vector bundle on the moduli space of vacua. So whenever I construct, one of the next ways of understanding what the moduli space of vacua is, that line operators give holomorphic vector bundles, or more generally quasi-coherent sheaves, on this moduli space. So again, in algebraic geometry, there's a tautological way to make that happen. You're going to declare a space, just like you do spec for a ring. You can declare a space. This is called the theory of Tanakian reconstruction. You can find a space on which line operators become quasi-coherent sheaf. And that's, again, a space that somehow lives intermediately between this mythical beast and the concrete affine variety I built. So this is going to be kind of the place where I'd like to work. Given a topological field theory, I get an affine variety and a more interesting variety, not necessarily affine, mapping over it. So if you're familiar with Rosansky-Witten theory, if you do this in Rosansky-Witten theory, this would be on a holomorphic symplectic manifold. You'd get the affinization of the holomorphic symplectic manifold, and here you'd get the holomorphic symplectic manifold itself. Okay. And you can keep playing this game. I won't subject you to that, but you can, instead of thinking about line operators, you can think about surface operators, or keep going on. And surface defects will give something more fancy, will give some kind of sheaves of categories over this moduli space. You can try to get a better and better understanding of what the honest moduli, what the theory is, by keeping track of more and more defects. And this is kind of the kind of ultimate statement of this kind is the version of this is the cobordism hypothesis. Which we've heard in a couple of talks about. And the cobordism hypothesis is kind of the ultimate statement. It says that the entire topological field theory can be completely recovered by its collection of boundary conditions. So that's some kind of extreme version of this. So that's a way I want to understand a topological field theory. You can probe it by understanding defects of various dimensions. I'm not going to go all the way down to understanding all the boundary conditions. I'm only going to seek some kind of shadow of the theory where I remember local operators and line operators. Okay. Is there a clock here? Is there? Oh. Oh, thank you. Okay, great, thanks. Okay, so now I'd like to apply this philosophy into a particular field theory, which is four-dimensional n equals 4 Super-Yang-Mills. I'm going to try to understand n equals 4 Super-Yang-Mills. Again, I'm only accessing things as topological field theories. So I'm going to following Kapustin and Witten's work in geometric Lagrange, I'm going to consider like two topological field theories, which I think Witten at some point called the A hat theory and the B hat theory. These are four-dimensional analogs of the A model and B model. So these are four-dimensional topological field theories. I'm going to call one of them, I'm going to fix a compact Lie group, G sub C. But my G is always going to be the complex group. So I'm going to write everything in terms of the complex, not in terms of a compact Lie group, but in terms of its complexification. And when you look at n equals 4 Super-Yang-Mills with this gauge group G sub C, and you do a particular twist, the GL twist, and you put a particular parameter in that twist to infinity, that gives a four-dimensional topological field theory called B hat sub G. There's another version called the A hat theory, which here I would consider the n equals 4 Super-Yang-Mills for the dual group with a dual parameter. I get another theory called this A hat theory. And the S duality, or the geometric Lagrange program, following Kapustin and Witten, is the statement that these two theories are the same. If I do the A twist of n equals 4 for the group G dual, or the B twist for the group G, those are equivalent four-dimensional topological field theories. Okay. So what I'd like to do is to take this, and so now I'm really thinking of I'm only thinking of there being one topological field theory with two realizations. I'm either going to think about the B model for G or the A model for G dual. So I want to take this topological field theory and try to understand what its moduli space is from the kind of point of view we were describing. Okay. So in order to do that, I need to start with what are local operators. Okay, so again, there's one theory, and in this theory we have the ring of local operators. Like in Donaldson theory, we have the cohomology of the equivariant cohomology of a point. the cohomology of the gauge group. So here we take the classifying space of my gauge group, and I take its cohomology. And those give me local operators. So these operators, I can describe the cohomology of the classifying space of a group as Weyl group invariant polynomials on the dual of the Cartan, or if you'd like, G invariant polynomials on the dual of the Lie algebra. Okay. So that's my ring. I have a commutative ring of just invariant polynomials. So for UN, this just means traces. I'll just look at invariant polynomials in my adjoint scalar. So this is my commutative ring. Now, I promised you that local operators were supposed to be this Poisson graded. So I'm in 4 dimensions. Local operators are supposed to be an odd Poisson algebra. It's very boring in this case. The odd Poisson bracket is 0. So we just have a commutative ring. Okay, so we just have a commutative ring with 0 bracket. So that tells me that my idea of the moduli space is this M-loc. Well, I'm just supposed to take this commutative ring and take its spec, but it's already given as functions on something. So the space of the moduli space is I'm assigning is just the space, the Cartan modulo of the Weyl group, just the space where invariant polynomials live. Right? So in other words, it's rank many copies of the complex numbers, which will be familiar to physicists, the Coulomb branch of n equals 4 super-Young Mills. So that's the moduli space I have, just if you like, configurations of endpoints in C, if you're GLN. Okay, so that's my space, but I'm going to think of it from the point of view of representation theory. I want to think of this as you take the Lie algebra dual, and you look at the space, the kind of the affine quotient of it by the group G, the space where invariant polynomials live. Okay, so far so good. Okay. So that's my local operators moduli space. Now I want to play this game of turning on omega background. So I'm studying 4-dimensional super-Young Mills, and I'm going to turn on epsilon 1 if you'd like. I'm going to rotate around some axis. This omega background in this case doesn't do actually anything interesting. The ring it becomes the same. The ring of local operators doesn't change at all. So that's in some sense a geometric statement. That's a reformulation of the Harish-Chandra isomorphism in representation theory. So when epsilon is 0, I have this ring of invariant polynomials. When epsilon is non-zero, I have the same ring, but I'm going to think about it as the center of the enveloping algebra. So Harish-Chandra's isomorphism says that the center of the enveloping algebra and the ring of invariant polynomials are both isomorphic to the same space of functions of the same space of traces. Okay. So that's the ring. So in other words, under this deformation quantization, I promise the omega background is a deformation quantization, the center, the Casimirs of this Poisson bracket, the Casimirs on G dual, or the center of the enveloping algebra, are the same. Okay, so now I want to go to line operators. All right, so we understand local operators. Let's go to line operators. So I'm going to start on the A side. So on the A, so again, they're going to be the same. Let's think about them from the point of view of the A side. So this is, again, explained in the work of Kapustin and Witten. The line operators in n equals 4 in this A twist are what are called the Tataki category, or the derived Tataki category in representation theory. So what does that mean? You look at the affine Grassmannian for your group here. It's a group G dual. So what is the affine Grassmannian? It's the quotient of the loop group by positive loops. So look at the loop group of G dual, it's quotient by positive loops, or if you like topologically, it's base loops in the compact group. And you look at equivariant sheaves on that. So that's the space that was explained in Kapustin Witten to match line operators in n equals 4. So this is the Tataki category, which probably looks somewhat unpleasant if you haven't seen it before. One thing that's nice about this, from the point of view of omega background, the omega background becomes something very simple. So maybe I should write that here. This affine Grassmannian is the loop group of the dual group modulo positive loop. And maybe I'm thinking about it equivariantly. So I'm thinking about it modulo positive loops. From this point of view, the omega background, the rotation just means you rotate the loops. This is some kind of space of maps from a circle. You can just, this is the circle you're rotating. So the affine Grassmannian carries an action of rotations, and studying line operators in omega background from this point of view means putting in, studying sheaves in the Grassmannian that are equivariant for loop rotation. Okay, so this is complicated object. On the other hand, it has a dual description, which is line operators on the B side. So on the B side, you have a much simpler story. What are line operators in this B theory for G? The claim is it's just the derived category of sheaves on G dual mod G. So you look at the Lie algebra G dual, and I'm going to look at coherent sheaves, or if you like, modules for holomorphic functions on G dual, and look at ones that are equivariant with respect to the coadjoint action. Okay. So I'm going to study again. So I'm taking G dual, I'm not doing mod mod. I'm literally taking the space G dual, and I'm doing G equivariant geometry on G dual. And if I look at coherent sheaves on here, I get, that's what the Tataki category is. In particular, let me say that if you had the derived category of just a point, inside of here there's the point, let's say 0 mod G. This is the category of representations of the group G. So these are the kind of familiar Wilson operators in this B theory. The representations appear here just living at the point 0, but we also have this whole Lie algebra dual appearing. Okay. Does this stay? Okay, now when you turn on omega background here, something a little more interesting happens. You replace the dual of the Lie algebra by the enveloping algebra of G. So I put in this parameter epsilon just to keep track that there's a parameter, but when you have just one epsilon parameter, there are only two things you could do. It's either 0 or non-zero. So if you'd like, you can ignore this epsilon. There's really, when epsilon is non-zero, you get just enveloping algebra. When epsilon is 0, you get functions on G dual. Okay. So this now really looks like deformation quantization. You take the dual of the Lie algebra, or if you like functions on it, which is a symmetric algebra of G, and you've quantized that, you replace it by enveloping algebra of G. So in other words, what this is saying is that line operators in this omega background are UG modules. UG modules just means representations of the Lie algebra, but representations of the algebra that are equivariant with respect to the conjugation action of the group. So this is called Harishchandra bimodules in representation theory. But I just want to think of it kind of maybe more informally as you take little g dual and you quantize it, and it's a quantization of little g dual mod G. Okay, so those are line operators. And then we have S-duality. S-duality says, well, these two pictures are going to be the same. Line operators in the A side are the same as line operators on the B side. Now, this is a theorem in representation theory. This is a theorem of Bezrukavnikov and Finkelberg. It's called the derived geometric Tataki theorem. And it says exactly that these two categories we had in these last two slides are equivalent, with or without epsilon. So both in and out of omega background. So how do I want to interpret this theorem? Well, or if you like, the theorem gives me a way of accessing the A side. So I'm going to really focus on the B side. So on the B side, this is my category of local operators in omega background, or without epsilon, that's my category of line operators. So that's telling me, what is this telling me? This is telling me how to think of my moduli space of vacua. It's saying that the moduli space of vacua, at least as seen by line operators, that's my M subline, is this coadjoint space, G dual mod G. So remember what happened before. When we used only local operators, we get the affine variety, which is the affine quotient of G dual. Now when we remember line operators too, we actually remember the whole space of G dual mod G. Right, so G sub epsilon is just a kind of a facetious way of saying when epsilon is not, this is the deformation quantization of this. So this is not really a space when epsilon's non-zero. So yeah, this space becomes a kind of a mildly non-commutative space. And it just means that it's a thing I know what sheaves on it are. Sheaves on it are representations of UG. Okay. So that's, yeah, maybe this is kind of, I don't know if that's useful or mnemonic or not. So, but in whatever case, I know that line operators are this, and I'm just duly interpreting that as saying that the moduli space is some quantum version of the coadjoint quotient. Okay. Now, what does this mean physically? I think a correct interpretation of this is that you have the space, the usual Coulomb branch, which is just the space given by these invariant polynomials, but there's some residual gauge symmetry along the Coulomb branch. And that's saying, from this point of view, if you want to study maps into the Coulomb branch, you have to remember this residual gauge symmetry. Mathematically, that's saying that the kind of corrected version of the Coulomb branch is a stack. That you're looking at maps into, the points have automorphisms, which give you the residual gauge groups. And the correct stack for n equals 4 in this twist is this stack, the coadjoint quotient of G. So it's some stacky refinement of the Coulomb branch we had before. Okay, so now I'd like to try to kind of understand this geometry of this space I'd like to sort of say, what can you do with this funny-looking space, and how are you going to model it, understand it, and how does it relate to Hamiltonian geometry? And there's kind of an interesting integrable system structure on this Coulomb branch. That's kind of a 4D analog of the usual integrable systems we see in moduli spaces of 3D gauge theories. So I'm going, if you like this language of shifted symplectic geometry, this space G dual mod G is really a shifted version of the cotangent bundle of point mod G. And so the cotangent bundle of point mod G would be the little Lie algebra little G dual sitting in degree 1, and now we've shifted it. So that means that whatever this funny space is, it has some kind of symplectic structure. It's a kind of a cotangent bundle, which means it has a kind of symplectic structure. That's what shifted symplectic geometry is there to provide. And not only is it a symplectic space, but it actually carries an integrable system. So there's this space of line operators carries a canonical map to the space given by local operators. That was what we had in general for any field theory. This space was really just this affine quotient. So here we have this picture. This is my Cartan mod W. This is the space given by local. Up here, I have a space which I'll try to draw a bit better in a second. There's a space given by line operators, which is the stack G dual mod G. And there's a map, which is this affinization map. And the claim is that this map is an integrable system in the shifted sense. This, without the symplectic geometry aspect, this map was really emphasized in the work of Ngo Baoqiu, and he kind of called this the mold for a whole family of integrable systems. Or actually, he says it's a moule, and for years I thought it was something about moule frite or something. I got very confused, but it means mold. So it's a place we're going to use it as a mold to build honest, usual integrable systems. Okay, so in other words, I'm going to try to unpack, this probably seems kind of an abstract beast. I'm going to unpack it to get some more concrete or regular integrable systems. So how are you going to unpack it? Well, you map things into it, just like John was saying. So I'm going to try to understand this map, or understand the two spaces, by mapping things into it. Okay. Oh, but before I do that, you can turn on epsilon if you'd like. And so you can do this. There's an analog of this map in the omega background, which is a kind of a non-commutative integrable system. So it's a map of mildly non-commutative spaces. And again, what do I actually mean by a map between these epsilon spaces? It really means that you can pull back sheaves. So it really means you have a functor from modules for the center, that's sheaves on this nice commutative space, to modules for this enveloping algebra. And there's an induction functor. So there's a functor from here to here, and that's a quantum version of this integrable system. So I'm going to call this a kind of some version of the Seiberg-Witten integrable system in 4D. Okay. So I'm going to try to understand, so how am I going to understand the space in a way that's more concrete? The way I want to make it more concrete is I'm going to map in ordinary Poisson varieties. Technically, I'm going to look at quasitropic maps from Poisson varieties. So I have a space X. I'm going to take an ordinary Poisson variety X, and there's a notion of a reasonable map to here, quasitropic map, to G dual mod G. So I'm going to take quasitropics in G dual mod G, maybe take two of them, an X and a Y, and I'm going to intersect them. So given every Poisson space mapping in here and another one, I can take their intersection, or if you like, their fiber product, and that's another Poisson variety. So I'm going to think of this as a kind of mechanism for producing a whole bunch of Poisson varieties by intersecting ones that are mapping in. And I'm going to, just because there appear a bunch, I'm going to call these beasts, let me call them G phase spaces. Why that's not a terrible name, not as terrible as it looks, I'll explain maybe later. So there's a class of spaces I'm going to get by just taking intersections of Poisson varieties in G dual mod G. Now what's cool about these guys? Well, by construction I said they're Poisson varieties, but they all come with a map to Cartan mod Val group, which are a family of Poisson commuting Hamiltonians. So you have a Poisson variety with a family of Poisson commuting Hamiltonians exactly parameterized by invariant polynomials. So each of these spaces carries such a map. And similarly, in the omega background, there's a quantum version of these. You have a bunch of non-commutative space with a bunch of commuting quantum Hamiltonians. So that's a sense in which it's going to be a mold in some sense, I think most classical integrable systems, finite dimensional integrable systems, arise by these kind of constructions. So I'll give examples, but all the classical examples, Toda, Calogero-Moser, etc., appear this way. So that's how rather than thinking abstractly about this stacky nonsense, I'm going to intersect and have spaces which are maybe honest varieties, honest Poisson varieties, with honest Poisson commuting Hamiltonians. Now this is, I claim, a reasonable thing to do from the point of view of physics as well. From the point of view of physics, I want to say I'm going to consider, I'm going to study boundary conditions in my four-dimensional theory. Of course, I don't have full access to, I don't know everything about boundary conditions, but I'm only going to understand as much of boundary conditions as I can by looking at line operators, but how the line operators are acted on them. But if I have a boundary condition, so for example, if I have a 3D n equals 4 theory with G or G dual global symmetry, I can cook up boundary conditions in n equals 4. And given a boundary condition in n equals 4, well, given two of them, if I have boundary condition 1 and another boundary condition B2, I can consider the four-dimensional theory reduced on an interval. So this gives me a three-dimensional topological field theory, which is, again, if you'd like, I'm considering four manifolds which are an interval cross something else, and at one end of the interval I'm putting one boundary condition B1, and another I'm putting boundary condition B2. Okay. And so this gives me a big family of three-dimensional topological field as I vary what B1 and B2 are. And each of these, being a three-dimensional topological field theory, it itself has a moduli space, which is a Poisson variety. And those modular spaces are exactly the same class I was talking about before. These things I was calling quantum G spaces, that intersection in G dual mod G, that's just another way of saying physically, look at the modular space of the 3D theory reduced on an interval. But I'm getting many interesting theories this way. For example, anything that comes from gauging a global symmetry of a 3D n equals 4 theory. So for example, 3D n equals 4 gauge theories. So the moduli spaces and their quantizations in omega background, these are exactly the kind of spaces I'm producing commuting Hamiltonians on. Okay. This picture will reappear in Tudor's talk. This is being explored with Tudor and Andy. Does this picture make some sense? So let me give two examples of boundary conditions. Kind of two basic examples. One is the Dirichlet boundary condition for the G theory. So I guess I want to be careful because I was identifying the G theory and the G dual theory. So I want to emphasize, look at the Dirichlet condition for the G theory. Mathematically, you know, if you wanted to give me a Poisson variety mapping to G dual mod G, the most obvious one is G dual itself. So take G dual mapping to G dual mod G. That's an example of an X I can consider. Okay? That's one of my Poisson varieties mapping to G dual mod G. So that's this Dirichlet boundary condition. It also has a quantum version, which is, again, the quantization of G dual means just representations of the Lie algebra. So look at the category representation of the Lie algebra. That's the omega background for this boundary condition. Okay. So that's a basic example. Now, what can you do with it? Again, what I proposed was that you should intersect with it. So now I've chosen one of my boundary conditions, and I'm going to put this Dirichlet as one of the others. So this is going to correspond to my space X. This is corresponding to the space that was Y before. So what boundary condition? You're supposed to sandwich it. So here I'm making a sandwich with Dirichlet on one side and X on the other. So what do you? Well, you get a Poisson variety. And you ask, what does it mean for a Poisson variety to come by this construction? And it's actually very simple. If you look at this Poisson variety, it has two natural things. It has a map, which I'll call the moment map, to G dual. And it has a G action, where the quotient is my original X. So if you think what the spaces you get this way, they're exactly the same as Hamiltonian G spaces. Again, I'm doing everything holomorphically, so these are holomorphic Hamiltonian G spaces. So a space X that appears here is in bijection. So the boundary conditions that I'm looking at, they're in bijection with just holomorphic Hamiltonian G spaces, and this is indeed the moment map. So this means that the boundary conditions, the kind of X's I'm getting, include any holomorphic G space, and the kind of sandwiches I get out of them include any kind of Hamiltonian reduction you can take of a holomorphic G space. So for example, the kind of spaces I can get at the corner here include, take the cotangent bundle of G and take any Hamiltonian reduction on the two sides by any two subgroups you want. So that's a class of spaces, and we're saying that all of these class of spaces carry a family of commuting Hamiltonians, which is, of course, this kind of classical constant method to construct integrable systems. And so this is just the setting for that. Does this make sense? Okay. You can also do a quantum version. I don't know how much to emphasize this. You could do a quantum version of pairing with this. So now we have a non-commutative space. And again, the non-commutative x's are in bijection with quantum Hamiltonian G space, so x tildes. So when you intersect with Dirichlet, you kind of ungauge the G symmetry. You get a notion of a quantum Hamiltonian G space. So you can define what you mean by a quantum Hamiltonian G space in several ways. I like to think of it as module category for D modules on G, or you can think of it as a category with a representation of the group G. But anyway, to make it a little less abstract, think of cotangent bundle of M for any holomorphic G space and quantize it. So quantization of, for example, any cotangent bundle holomorphic G space, that's an example of a quantum Hamiltonian G space. And so this mechanism constructs commuting Hamiltonians. The center of the enveloping algebra produces commuting Hamiltonians. This is something very classical. Right? This is example is the Harichondra system of commuting operators on a locally symmetric space. You look on a quotient of a group G, you get a bunch of commuting differential operators coming from the center of the enveloping algebra. So it's just saying that in a really complicated way. Okay, great. Let me mention another basic boundary condition. That's the Neumann boundary condition for the dual group. But the dual group is more confusing, so let's just think on this side. The map from G dual mod G to H mod W has a beautiful section called the constant section. So there's this map, so maybe I should let me draw a picture here. So here's my invariant polynomials. And here is an attempt to draw G dual mod G. I don't really know how to draw G dual mod G, so basically I'm going to draw G dual. So I think of G dual, so over the origin I have, I don't know, I have the kind of cone of nilpotent elements. So this is nilpotent elements in the group, and here I have regular elements. So maybe I'm drawing SL2. So this is one-dimensional, and I have one-dimensional family here. And the constant section, if you'd like, it's a section like this. This is the constant section. So there's a section, a map back from here, and I'm drawing it this way to just emphasize that it misses the bad points. So in SL2, it's going to miss the origin 0. Its image consists of regular elements in the Lie algebra. So I'll talk a little bit more about regular elements in a bit. But this is a perfectly nice the Poisson space. Okay, it has a 0 Poisson bracket, but that's not a problem. And here's a map from a Poisson space to G dual mod G. So that's an example of one of my boundary conditions. This is also called the regular nonpol boundary condition from G. And there's a quantum version of this which goes by the name Whittaker, but it's probably better not to subject it to that. But again, just like before I intersected with Dirichlet, I can intersect with Neumann, or sandwich with Neumann. Sandwiching with Neumann is gauging the G dual theory. I have a G dual theory. B is now a G dual a theory with G dual symmetry. I sandwich it with Neumann. That means I'm gauging the dual group. But from this point of view, it just means intersecting with the constant slice. I have my X to G dual mod G. I'm going to intersect it, just restrict it to the constant slice. And what I get there is exactly the Coulomb branch of 3D gauge theories. This is the construction of how you see Coulomb branches of 3D gauge theories. X corresponds to something of G dual gauge theories. X is some space with corresponds to something with a G dual symmetry, and this is the Coulomb branch of the gauge theory. And you see the integrable systems carried by these 3D Coulomb branches. Though I should emphasize again that this only sees, so to speak, the boring part of G dual mod G. It only sees the regular locus. It misses kind of the most tricky parts. Okay. So that's kind of the setup I want to work with. And now I want to tell you about what the kind of the new story is. Any questions before I move on about the kind of framework? Okay, so what I'd like to talk now is about integrating Hamiltonian systems. How to take a Hamiltonian system and integrate its flows. So you say, what do I mean by integrating a Hamiltonian system? So when I think of a Hamiltonian system, I don't know if I'm not brave enough to follow McLean. I'll just erase. So what do we mean by an integrable system? We have a family of, typically you have maybe some family of tori with some degenerate points. So here's a base of an integrable system, and maybe away from some bad locus, there's a regular locus of the base. So in typical integrable system, you have away from some bad fibers, you have a symplectic family of abelian, the alluvial tori. So you have a family of abelian groups over some open locus, and then they degenerate somewhat. So if your degeneration is not bad, the degeneration here we have maybe an elliptic curve. The degeneration here still contains C star, has an open dense locus, which is an abelian group. So in a typical integrable system, you have a family of abelian groups, and when they degenerate, you still have, at least as a dense locus, an abelian group. So in fact, what you get out of integrate the system. So what do I mean by integrate the system? You can take the infinitesimal flows given by Hamiltonians, and you can make it into a group action. In other words, there's a family of groups over this base. So here's my base B. That's the base of the integrable system. I have a family of groups, which I'll call J. So in this case, it's the family of elliptic curves degenerating to C star without the singular point. Right? So I have a family of groups, and it acts on the total space in such a way that it exponentiates the infinitesimal flows by Hamiltonians. Okay? So that's what I mean by an integration of an algebraic Hamiltonian system. It's a family of abelian algebraic groups whose action integrates the flows. Okay. Let me say a little bit more about this regular locus here. So inside of here, I have this regular locus, G dual reg. Now, what does it mean to be regular? Means that the centralizer of your element is the smallest dimension. It's an element of the Lie algebra whose centralizer's dimension is rank. It makes a centralizer abelian. So if you look at regular elements, they have centralizers which are abelian groups. And this is a big open locus. So in SL2, for example, the regular locus is everything except 0. Every element in SL2 is regular except 0, whose centralizer is all of SL2. So for SL2, maybe I should draw this. You have, if you have here's the regular, if you have the regular locus, you get, how do I draw this? You have a kind of point with a stabilizer. The stabilizer of a generic element in SL2 is C star. The stabilizer of a regular nilpotent matrix is 2 copies of C, or C cross Z mod 2. So you have this family of the regular elements whose stabilizers are C star or C union C, and then there's this annoying point 0 whose stabilizer is this big non-abelian group SL2C. Okay, so this is, if you'd like, a better picture of this Coulomb, stacky Coulomb space. So most of it looks like point with the symmetry of C star, point with the symmetry of C star, point with the symmetry C cross Z mod 2, and then there's some really bad point with a non-abelian symmetry. But there's a nice open dense locus where the symmetry is an abelian, where the residual gauge group is abelian. Okay. So that's called the regular locus, and that's where this constant section. So we can look, this is what we already drew here, was this family of regular centralizers. What are regular centralizers? These are this centralizers of regular elements. That's a family of abelian groups. So there's this family called J over this Coulomb branch. This family of centralizers, the phi brat lambda is the centralizer of the element on the constant slice with characteristic polynomial lambda. So it's a nice constant dimensional family of abelian groups over this base. And in fact, the whole regular locus in G is generated by the cosine section. It's an orbit of the section. So the entire regular locus in G really looks like just the quotient, the classifying space of this group J. So you look at Cartan mod W, the regular locus over it just looks like a family of shifted abelian groups. So this is a precise sense, if you'd like, why that map I claimed was kind of a shifted integrable system. What does the map look like? It really looks like G dual mod G mapping to the base. It really looks like point mod C star, point mod C star, point mod C star, point mod C cross Z mod 2, looks a family of classifying space of abelian groups. So it looks like just like an integrable system should, a family of abelian groups. And then there's some bad points. Okay. All right. Now, in his proof of the fundamental lemma, Ngo proved the kind of fundamental lemma of the fundamental lemma. And his fundamental lemma was the following statement, that if you look at this group of regular centralizers, this classifying space of regular centralizers, it's a group, so they act on themselves. But he showed that they act on all of G dual mod G. So what is this? Let me try to draw this picture here. We have this locus G dual mod G. Inside of there's an open dense locus, which is actually a group. It's a family of abelian groups, just like you imagine an integrable system looking. So you have a family of abelian groups. That's an open dense locus. And what he showed is that family of abelian group actually acts on the whole space. In other words, he integrated this integrable system. He provided integration. And his proof was kind of funny. It's just Hartog's. You just look at the complement of codimension is codimension 3. So you already know what this is away from the regular locus, and you just extend. So away from classical groups, there wasn't kind of a priori description what this action is. Okay. So that's Ngo's integration. So what is it good for? Again, let's try to unpack this in a less abstract way. It tells you that any of the families of Hamiltonian flows we were constructing, we said there's a whole bunch of commuting Hamiltonians on all of these G phase spaces. All of those families can be integrated. So there's a family of abelian groups over this Coulomb branch that acts on any of our Poisson spaces, integrating the flows. So in other words, any Hamiltonian system you get, whether or not it has the right dimension, if your construction of the commuting Hamiltonians came from the Casimirs in the Lie algebra, by some Hamiltonian reduction, you can always integrate it in the sense that there's a family of abelian groups of the right dimension integrating the flows. So it's kind of a universal integration of all G systems. So in particular, again, any Hamiltonian reduction of the cotangent bundle of G, or if you'd like the moduli space of any 3D gauge theory, 3D n equals 4 gauge theory, though for this you don't actually need Ngo because that only uses the regular locus. But you have a family of abelian groups integrating any of these Hamiltonian systems. Okay, so now I can finally get to well, maybe I should mention what Ngo uses this for. He uses this in the case of the Hitchin system. And maybe I just emphasize that this integration is not something you'd come up with just by literally trying to exponentiate vector fields. For example, these groups, these J's are disconnected. This group has two connected components. So it's not something you could get just by using the Lie algebra, and that's exactly the whole point in the proof of the fundamental lemma. It's all about the action of groups of connected components of this on cohomology of Hitchin fibers. Okay. Okay, so now let me just try to say what we do with Sam Gunningham. So what we do is we give a geometric construction, kind of a priori construction of Ngo action, but maybe more importantly, we quantize it. So we give a universal integration of these kind of non-commutative, of these quantum integrable systems. So what does that mean that we quantize this action? That means we give a commutative algebra of line operators, or more precisely, a commutative tensor category, which we call the constant category. So I'll tell you what it is. There's a symmetric monoidal, or commutative tensor category, which at epsilon equals 0 is just sheaves on this J, on Ngo's space J, just quasi-coherent sheaves with convolution. Epsilon non-zero, something cool happens, and that's sort of why things are interesting. Epsilon non-zero, this sheaf deforms to sheaves on the Cartan modulo the affine Weyl group. Or if you like, instead of if you think analytically, instead of Cartan-Lie algebra mod affine Weyl group, you can think of the dual Cartan group mod W. So at epsilon non-zero, we look at quasi-coherent sheaves on group Cartan mod W, and it acts. Where does it act? We show that this acts on our Coulomb branch, or if you, in a central way, or equivalently, this means it acts on all of our phase spaces, all our quantum G phase spaces, all of these derived of these intersections. It acts on all of them in a way that deforms the action of J. So you quantize this and go integration. So what does this mean? It means that if you look at line operators at n equals 4 in this twist, they have a kind of hidden symmetry. They carry an action of a commutative algebra of operators. And in particular, this commutative algebra of action gives you get a commutative action on any quantized moduli space of any of these 3D theories you get by reductions, for example, 3D gauge theories, or you can kind of integrate all Hamiltonian G spaces in a universal way. So let me kind of just say some words. What is the meaning of this affine Weyl group? Where does this come from? So the statement is really saying that if you have one of these quantum G phase spaces, it lives over lives over the Cartan modulo the affine Weyl group. So I want to claim that naively you might have guessed that that these quantum spaces live over Cartan mod W. They don't. They live over Cartan mod WF. So what's the difference between Cartan and between W and WF? It's translations. So let's just be very explicit. Take the group to be C star, right? If you look at the group, so the simplest example of this Harishchandra system, you look at the eigensystem of the only invariant differential operator on C star. You look at Z d dz f equals lambda f. That's your eigensystem. Or equivalently, you can look at the flat connection with a regular singularity, d minus lambda dz over z. Now, when you write these things down, you see a lambda in there, which is a complex number. So when you write it down, you think that those systems might be parameterized by lambda. But you know that's not true because of gauge invariance. This system's if you shift lambda by an integer, you get the same equivalent system. So there isn't an intrinsic parameter lambda here. The only intrinsic parameter is the monodromy, is x of 2 pi I lambda, which lives in C star. This is my dual Cartan. Or if you'd like, it's the class of lambda up to translations. So this is the fundamental feature of quantum integrable systems, is you have some translation invariance. This appears in representation theory. For example, if you look at representations of a Lie algebra, there's a natural parameter you might think of, which is the action of the center of the enveloping algebra. But the category of representations depends intrinsically not on lambda, but only lambda up to translations. This is the theory called theory of translation functors. Or if you'd like, if you study locally symmetric spaces and you look at the eigensystems of these higher Laplace operators, these Harishchandra systems, the eigensystems themselves depend on lambda only up to translations. This is this theory of these shift operators. So the fundamental parameterization for these systems of differential equation, it lives in some quotient of these lambdas by translations. So that's what our theorem provides in a universal way. It's kind of a categorified version of these systems. It says that any of these categories, like representations of Lie algebra, system of differential equations on these homogeneous spaces, line operators on 3D gauge theory in the omega background, they all live over this quotient. Do I have a couple minutes or no? Not really. Maybe let's just stop. Oh, 2 minutes? Okay. Let me just say that the construction is actually super easy. I kept mentioning the A side. One of the nice things about this proof and the construction of this in Go map, we give a construction that's extremely simple on the A side. So everything I talked about was really happening on the B side. But on the A side, there's something really nice you can see. So this Tataki category was some complicated category of sheaves, which we don't need to peer into the guts of. But the point is that on any space, any category of sheaves that you have, you can always tensor it by vector bundles. In this case, you can always tensor by local systems. So this whole category of line operators has some extra symmetry, which is you can just tensor them by local systems. And that gives this commutative symmetry. So when you look at what these local systems are, and you use the work of Bezrukavnikov, Finkelberg, Merkovich to identify the equivariant homology of the Grassmannian, you might find that these local systems are exactly representations of this group J. They're exactly the sheaves of Bj. So the action, this J action on the dual side, on the A side comes very nicely from just some simple geometry, and the same works with omega background. So you can construct this category. So let me just give a couple of descriptions. You can define this category as some category of modules for this homology. You can call it the quantized phase space of the total lattice for G. In terms of representation theory, it's what's called the Whittaker-Hecke category, which means line operators in 3D n equals 4. Or you can make this very concretely. You can describe this category extremely concretely. It's modules for this affine nil-Hecke algebra, which is a very simple algebra you can write down explicitly. And recent works of Lonergan and Ginsburg identify this exactly with this category with exactly sheaves on Cartan mod W. And once you have this, you can now, there's a lot of things that you can try to do with it in the geometric Langlands program, in geometric representation theory, and I think most interestingly in the study of homology of character varieties of surfaces. So basically anything that you can fit in n equals 4 in the GL twist has this extra symmetry, and you can try to use it. Thank you.